All right, for this lesson, we only have one more example. So in example one, we did a very basic quadratic regression. Here, let's do an application quadratic regression. So it says example two, partially because of Americans living longer, the number with Alzheimer's disease and other dementia is projected to grow each year. The table below gives the millions of US citizens with Alzheimer's from 2000 and projected to 2050. So part A wants us to create a scatter plot with X equal to the number of years after 2000. And if I get a different color here, Y equal to the millions of Americans with Alzheimer's disease or other dementia. And so there's what my two variables represent. So we're going to get into Desmos. We're going to create the scatter plot, but we do have to deal with this X equaling the number of years after 2000, because right now we have 2000, 2010, 2020, 30, 40, and 50. And I'm not typing in those numbers here. How many years after 2000 is 2000? This one here, I'm just going to kind of cancel out those numbers. That one's 0. How many years after 2000 is 2010? That's 10. How many years after 2000 is 2020? And that's 20. And so then so on. This will be 30, 40, and 50. So those are the numbers I want to type in. And so let me split screens here. And I'm going to get rid of all this. This was the last problem for example one. I want to just go back to home right here. And let's create the scatter plot. So add an item, table, and enter your numbers. And once we do 0 and 10, it's going to start guessing on us. And so then let's put in our Y values. Okay, and before I do my zoom fit, I'm going to take the 3 seconds it takes to check my data. And so we have 4, 5.9, 6.8, 8.7, 11.8, and 14.3. So I like my data. So I will hit my zoom fit, and there is my data right there. Now this is another one like example one where we could probably say that a line would fit that, but it does tell me here on part B to find a quadratic model. So it's not even letting me choose which model, even though it does look like it kind of could be a line. They specifically want a quadratic model. So B says find the quadratic model that models this data. Report the model with 4 significant digits. I believe if you have to take chemistry, you're going to get real familiar with significant digits. I do have an additional lesson over significant digits. If you don't know what significant digits are, it should be in this playlist right before this examples, in between examples 1 and 2. So watch that video if you have no idea what a significant digit is. But I'm going to assume we've all watched that video or have had chemistry and are familiar with it. So let's get back into Desmos and get my model. Let's go over here. And just get rid of this. Okay. So we'll go down into our second line. And we have y1 tilde x or ax squared with a 1 plus bx with a 1 plus c. Okay, if you forget any of these little subscripts, you're going to get this caution sign, this warning sign. Make sure those all have subscripts. Okay. Let me zoom in some. Okay. So we can see that data. And most of it's pretty much on that line, except for this. This is kind of maybe a small, like little outlier just because it's the furthest one. But everything else, it's touching that pretty good. So what is my answer here? Okay, here is my A. So these first two zeros do not count. So we have 2107. I'm gonna write, can I highlight just part of that? My A equals, yes, that right there. So we have Y equals 0.00. So those don't count as my first two digits, but then 2107 is my four significant digits to x squared plus 0 point. So on this one, this 0 doesn't count. So we have right there, and that 5 will make that 8 go up. So 0.977, and again, that rounds up to a 9, and that goes with my x. And then C, this 4 does count as the first significant digit. So this will be right here, plus 4.207. So there is my quadratic model with 4 significant digits. Okay, now we kind of already talked about this line right here, and that it is a good line. It does say graph the data on the model on the same axis, so that already happens here on Desmos when we make that regression. And it wants us to comment on the fit. Now, honestly, I don't really look at this. I mean, I did look at it, and I did comment on it. But if you look at this R, or R squared, that tells you everything you need to know. Here, my R squared equals 0.09926. Remember, the closer that this R or R squared is to 1, the better that this fit is. So the fact that this is 0.0, oh, let's try to switch that 0, because that would not be a good fit. Since it is 0.99, 0.99 is very, very close to 1. So this is a really good fit. And so that's what I exited out of on that snippet. I just added this to our notes. It wants to know then, is this a poor fit, a mediocre fit, an excellent fit, or a good fit? Your answer is always going to be good. And there's not really much more to say about that. I'm guessing that the difference between excellent and good is it's excellent if it equals 1. So an example 1, our R squared equaled 1. That's an excellent fit. But because this doesn't equal 1, but it's very close to 1, it's a good fit. Now, what separates a good from mediocre? I don't know. What separates mediocre from poor? I don't know. But your answer will always be a good fit. Okay, spoiler alert. Now, up until this point, that's what we pretty much did for example 1. But now we have questions going with the context of this problem. It says, how many Americans did the model, which my model, let me do this. My model is this right here. That's my model. How many Americans did the model predict will have Alzheimer's disease or other dementia in 2056? Okay. So in 2056, first, is this giving me my X value or my Y value? Well, X has to do with the number of years after 2000. When I'm talking about time, if I'm talking about the year, that's my X. Now, X isn't just the year, X is the number of years after 2000. So how many years after 2000 is 2056? That is 56. And so we did 2056 minus 2000 to get there. So we're going to type this in, and we are going to find the intersection. to get our answer. We went over this last regression, but it wants the model. This is my model, right? My answer will differ slightly if I do not use the model. So I am not going to put x equals 56 into this third line. I first need to type in my model and get off this regression because I cut off these digits, right? I cut off that 1, 4 at the end of this one. I cut off the 5, 7 on the end of this one, and I cut off the 1, 4 on the end of this one. So this has too many digits according to my model. This one is more accurate, but it wants the model. So we're going to go y equals, and let me split screen again real quick. I am typing in what I put for part B. Okay, pause the video if you need more time. But after I type in my model to this line 3, I'm going to unclick off of my regression. So now I just have my model on my screen. Then in line 4, I will put in x equals 56 and find that intersection point. So my intersection point is 16.29079. This doesn't tell me how to round. So I'm going to round. I'll just write them all. So we'll have 16.29079. Now, word problems need word answers or at least units. I found that y coordinate, what does my y represent? Y is equal to the number of millions of Americans with Alzheimer's disease or other dementia. So if it's wanting to know how many Americans, it's 16.29079 million Americans. I'll do millions of Americans. But word problems need word answers or at least units. Okay. And I might even go ahead and write in here. This is my line 4 because in Desmos, this became my new line 3. And let's just see, if I don't use this model, and sometimes it doesn't matter, but sometimes it does. If I use the regression and not my model, my number is literally just slightly off. Instead of 16.92, now it's 114 instead of I had 097. Does it make that huge of a difference? No, in the grand scheme of things, it's not that big of a different of an outcome. But my math lab's not going to accept this answer. It's going to accept this answer right here. So slightly off, but it will make a difference on you having to redo the problem. Okay. So last one. In what year after 2000, so that should tell you what variable we are searching. If it wants to know in what year, it's saying you're finding X this time. Does the model, again, predict that 10.2 million Americans will have Alzheimer's or other dementia? We are going to round up to the nearest year. Okay, so in what year? I know I'm finding X, and we've already established that Y is the number of millions of Americans. So if they're giving me this 10.2, this is my Y. And I don't need this one in here anymore. So I'm going to take away this one, and this is going to be my line 4 right here. Okay, so then we will find the intersection. And then we'll get to our answer. Okie dokie. So take away that one. We are given our y value and it equals 10.2. And I have unclicked off of my model and onto my regression. So I'm going to switch that. And here's that intersection. So we get 34, I'll say 0.96. Okay, is my X value here. But it tells me them to round up to the nearest year. So that will be 35. But it wants to know in what year after 2000. So it's after 35 years, but what year will that be? This will be in 2035. Because that is 2000 plus 35. Now, I do want to make a note. This one wouldn't matter which one you use because that's so close to 35. So if I click off that one, click on my regression, that still is going to round up to 35. So that one won't make a difference. It does on the previous one. I do want to make a note though, when we round up, it really doesn't matter what that decimal is. That's always going to go up to the next year. For example, let me get a sticky note here. Let's pretend instead of 34.96, let's pretend that I got 34.02. This right here, because it is rounding up, would still be 35. If I technically round, this rounds to 34, but if I am rounding up to the nearest year, it's going to be 35. So rounding up means take whatever that number is and go up to the next whole number, regardless of what the numbers are after the decimal.